Hi, in this fourth video, we'll wrap up all the things we've learned, the null and alternative hypothesis, the z-score, as well as the p-value, and kind of bring it all together to learn about significance testing and what it means to use the p-value to either accept a null hypothesis or reject it. Let's begin. Now that we have learned a bit about the p-value, let's talk about significance level and conclusions. Just a quick reminder from last session, but remember that p-value rests on the assumption that the null hypothesis is true. It is the probability of the data given the null hypothesis and not the probability that the null hypothesis is true given the data. Okay, with that out of the way, let's talk about significance level. So researchers will often refer to the significance level of a test, although it is not ideal to draw too firm of a line for significance, but we do have some benchmark that is globally used. So these benchmark that are often applied are when p-value is greater than 0.1, the observed difference is said to be not statistically significant. And when p-value is greater than 0.05 but less than 0.1, the observed difference is said to be marginally statistically significant. And when p-value is greater than 0.01 but less or equal to 0.05, the observed difference is said to be statistically significant. And finally, when the p-value is less than or equal to 0.01, the observed difference is said to be statistically highly significant. Another way to look at this is to define alpha as the chance that you are willing to take in mistakenly rejecting the true null hypothesis. If we agree to reject the null hypothesis only when p is lesser than or equal to alpha, we limit the false rejection rate of the null hypothesis to no more than whatever our significance level is. For example, by setting alpha to 0.05, we are willing to make a false rejection of the null hypothesis no more frequently than 1 out of every 20 tests. And if this is not cautious enough, we may draw a line at 1 in 50, which is 0.02 alpha level, or even 1 in 100, which is 0.01. Or whatever you're comfortable with. The jargon is to say that results are statistically significant when p is less than or equal to alpha, and conversely, when p is greater than alpha, the results are not significant, right? Not statistically significant. Beware though that the failing to find statistical significance is not the same as accepting the null hypothesis is true. It is merely saying the evidence is not strong enough to say that it is unequivocally false. So let's look at our distribution again to get a better understanding. Here on the y-axis is the probability of the observation happening. So how frequent do we see these observations? And then on the x-axis is all our possible results that can fall on the distribution. And let's go with our examples with the men's body weight that we've been using. And let's remind ourselves that the null hypothesis is saying that there's no difference in the men's weight from the 1990s and now, and the weight and the age range for these men are, remember, 25 to 35. And then the alternative hypothesis is saying, yes, there actually is a difference, right? With that, let's say we collect our observations, and then for this example, we happen to have a sample mean of 190 pounds. So remember, this is the average weight of men that we collected for 2021, ages 25-35, right? This 190 pound sample mean would fall right here. So remember, 170 pounds is in the center here, and 190 would all be over here in this far right. If we then set our alpha to 0.05, which let's just say it's here on this red dashed line representing our 95% statistical significant threshold, we then observe a result here. And we calculated a p-value for our statistical test that resulted in a p-value in this shaded region. So this observed probability value in this area to the right of the observed results, for this example, we can just say that the p-value is 0.03, which is less than our alpha, our significance level of 0.05. So this is a significant result. And what this ultimately means is that we're confident enough with this sample to reject the null hypothesis that there is no difference in the weight of men ages 25-35 from the 1990s and now. And we get to accept the alternative hypothesis that there is a difference. So with a p-value of 0.03, remember we're saying that we're 97% confident that this is true, that we're accepting the correct alternative hypothesis. And if we were to be wrong, it would be by the off chance of 3% that this was due to randomness. Thank you.